Hi, I'm Rebecca. During this lesson, we're going to concentrate on multiple angle identities. Let's look at our specific objectives. We're going to look at double angle identities, half angle formulas, solving equations, and product to sum and sum to product identities. Let's jump right into it by looking at our double angle identities. The first one we want to consider is the sine of 2 theta. Now notice that this value of 2 is not going to be a factor that can somehow be just factored out. Instead, we have to think of this in a formula format. This is equivalent to 2 times the sine of theta multiplied times the cosine of theta. For the cosine of 2 theta, it turns out that we have 3 different identities that we could use. The first one is that the cosine of 2 theta is equal to the cosine squared theta minus the sine squared theta. The next two can be arrived upon by using that Pythagorean identity in order to replace either sine squared theta by 1 minus cosine squared theta and then rewriting it as 2 cosine squared theta minus 1, or by taking this identity and rewriting cosine in terms of sine with the Pythagorean identity, and that would yield 1 minus 2 sine squared theta. The third double angle identity deals with tangent, and we can rewrite the tangent of 2 theta in the format 2 times the tangent of theta divided by 1 minus tangent squared theta. Now, we're going to start in on working with our first example. If we're given that the cosine of theta is equal to negative 12/13, and we're told that the sine of theta is greater than 0, we want to find the sine of 2 theta, the cosine of 2 theta, and the tangent of 2 theta. Let's begin by working with the sine of 2 theta. We're going to write down the formula as was given. Sine of 2 theta is equal to 2 times the sine of theta times the cosine of theta. Now notice that in order to evaluate using this formula, we're going to end up having really 3 things to substitute for. Well, of course, here we're given the value of 2. That's one of our factors. The sine of theta is going to need to be found. It's not given to us. The cosine of theta we're given is equivalent to negative 12/13. So what we're going to do is concentrate on figuring out what the sine of theta is equal to in order to be able to evaluate this particular function. Now, what we're going to do is start by drawing a picture. And so what I could do is draw a picture. Notice I'm told that sine of theta is positive, but cosine of theta is negative, which means that we're going to be dealing with an angle in the second quadrant. Now, I'm going to draw in an angle in the second quadrant. I'm going to drop a perpendicular here, forming that right triangle, and that I can use in order to evaluate by this particular given information. That is, I know that the cosine is equivalent to the side adjacent divided by the hypotenuse. So for that reason, I can label, in relation to this reference angle, our side adjacent as 12 and our hypotenuse as 13. Now, we can think of this movement to the left as being a negative, so we could actually label this as a negative 12 if we'd like. The reason we want to do this is to find this vertical length because of the fact that in order to evaluate the sine of this angle, we would use the opposite over the hypotenuse. So we would use the Pythagorean theorem in order to find that value. And in doing so, we can say, well, our y value is going to be found by taking y squared plus, we have our negative 12 squared equals 13 squared. Here we're going to have y squared plus 144 equals 169. Y squared equals 25, and therefore we can find our y value as a value of plus or minus 5. In this case, it'll be a positive 5 as our y value is positive. Using this diagram, then, we can find that the sine of theta is equal to the opposite over the hypotenuse, that is 5/13. Now, let's simplify this expression further just by multiplying out. We can think of the 2 as being 2 over 1. We're going to have 2 times 5, which is 10, multiply that times the 12, which we can think of as 120. We're going to pick that negative sign up, positive times negative gives us a negative result. And 13 times 13 gives us 169. And so we've been able to evaluate the sine of 2 theta by using this formula. Now we're going to go a little bit further and look at evaluating the cosine of 2 theta. So to evaluate the cosine of 2 theta, remember that we had 3 different choices. Since we've already found the sine of theta in our previous problem, then what we're going to do is use that first formula. We can write this down as cosine squared theta minus sine squared theta. Now, of course, you have options here. One option would have been if I had not already found the sine of theta, I probably would have wanted to use that format of the problem, which just required me to use the cosine of theta. Recall that we had 3 different formats for this particular double angle formula. Here, though, I can go ahead and substitute in values that are known. Remember, this means the cosine of theta squared minus the sine of theta squared. Substituting for cosine of theta gives us a negative 12/13 squared minus, and here we're going to have 5/13 squared. And let's evaluate further. We're going to come up with negative 12/13 squared, which is equivalent to 144 divided by 169. And we're going to subtract from that 5 squared, which is going to be 25, over 13 squared, which is 169. Subtracting then gives us a value of 119 divided by 169. And next, for the third part of the problem, we'd like to evaluate the tangent of 2 theta. Now, our formula, as you recall, is tangent of 2 theta equals 2 times the tangent of theta divided by 1 minus tangent squared theta. So notice that in order to evaluate this, we're going to have to find the tangent of theta. If I quickly sketch out the diagram that we had previously, you recall we had a 5, we had a negative 12, and we had the 13. And I'm going to use the tangent of theta as being equivalent to the opposite side, which is 5, divided by the adjacent side, which is negative 12. So negative 5/12 will be what we're working with. Here then, we're going to evaluate this as 2 times negative 5/12 divided by 1 minus our negative 5/12 squared. Let's simplify further now. Here, we can multiply in the numerator to come up with a negative 10/12. We'll divide that by 1 minus, we're going to have 5 squared, negative 5 squared, which is 25, divided by 12 squared, which is 144. Let's go further now. What we note is that we could simplify both numerator and denominator by multiplying both numerator and denominator by 144. This is going to be a quick way to get rid of those complex fractions. Here then, we're going to end up in the numerator noticing that the 12 will divide out with the 144, and we'll end up with our other factor of 12. We'll multiply that times negative 10 to give us negative 120. In the denominator, we'll end up having to do a distributive property. 144 times 1 will be 144, minus this fraction 25 over 144 times 144, which would be minus 25. And then we come up with a negative 120 divided by a 119. And that gives us our value then for the tangent of 2 theta. Now what we'd like to do would be to support our results by using the calculator. So let's see how to do that. We're going to start by thinking about finding the angle that we're actually working with. And so if we look back at the problem as it was given, what we notice is that we were given the cosine of theta was equal to negative 12/13. That means that the theta that we're working with is equivalent to inverse cosine of negative 12/13. Now, we don't really have to use the calculator to find this value, but it's just nice to see what it is that we're actually dealing with at this point in time. And so what we might do is use the calculator, and what this will verify is that actually we were working with a quadrant 2 angle. Here I'm in degree mode, and I'm going to be looking at the inverse cosine of negative 12/13. We come up with a value of 157.4 degrees approximately. And so again, what this basically tells us is we were working with that second quadrant angle, which is what we had worked with earlier when we drew our diagram. The other thing that we can do now is just to use that expression for our value of theta. And so we're not going to use the approximate value. We're going to use that inverse cosine. Let's write down, first of all, how we're going to deal with that. We're going to take the sine of 2 theta and replace theta with this expression. So this will be the sine of 2 times the inverse cosine of negative 12/13. Now, if I put this on a calculator, what's going to happen is I'm going to need to have parentheses around this entire angle that we're working with. So we're now going to go to the calculator and insert this expression to see what we come up with. We're going to have the sine of 2 times the inverse cosine of negative 12/13. And we have to close our parentheses twice here. Now we come up with this expression, but we can actually ask the calculator to change this to fraction mode to give us back the result as we had seen previously for our sine of 2 theta. Let's do the same thing for the other expressions. We had the cosine of 2 theta, and we're going to replace theta with inverse cosine of negative 12/13. And again, we'll change this to a fractional format, 119 divided by 169, which verifies our result. And finally, let's do the tangent of 2 times theta, where theta is inverse cosine of negative 12/13. And again, change to a fractional format, which again we can see is a verification of what we'd already worked with. Now we're going to move on to another expression, and in this case we want to use a double angle identity again. In this problem, we want to use a double angle identity to evaluate the expression sine of 2 times inverse cosine x over 2, where we're given that our x value is greater than 0. Now, in order to do this, we need to think about, again, the format of what we're working with. This expression, inverse cosine of x over 2, you'll recall is giving us back an angle, and I'm going to call that angle theta. So really what we have here is sine of 2 theta. So therefore the formula we're going to work with is going to be 2 times the sine of theta multiplied times the cosine of theta. Now let's think about how we can proceed. Remember that if I write down inverse cosine of x over 2 equals theta, then what I mean is that I have an angle theta so that the cosine of theta is equivalent to x over 2. Now, because I'm told that I have an x value that's positive, what's going to occur is I'm going to draw this in the first quadrant, because inverse cosine needs to have a value between 0 and pi, and for it to be positive, we're working in quadrant 1. So let's sketch out a diagram of what we can work with given this information. What I'm going to do is quickly just sketch out a right triangle setup here. And what I'm going to have is an angle theta. For this angle theta, we have the adjacent side can be thought of as having a value of x. The hypotenuse can be thought of as having a value of 2. Now, what I'm going to have to do in order to finish off this expression is think about finding this vertical length, because what I need to have would be a setup where I can substitute for the sine of theta and for the cosine of theta. In order to find that, I'm going to use the Pythagorean theorem. I can say that x squared plus, and I'm going to call this y since it is a value going upward here, y squared is equal to 2. Here I'm trying to solve for my value of y. Y squared is going to equal, sorry, that's 2 squared. That's a Pythagorean identity, of course. 2 squared, which is 4, minus our x squared value. And so y is going to equal either plus or minus the square root of 4 minus x squared. And in this case, it'll have to be positive because we have our first quadrant angle. And so this y value is positive, which means I can label this vertical side with square root of 4 minus x squared. Now, let's go back to the problem at hand. And what we can do is use this identity and substitute. We're going to have that this is equivalent to 2 times the sine of theta, which can be found by using this diagram as the side opposite over the hypotenuse. That'll be the square root of 4 minus x squared divided by 2. And then we're going to multiply times the cosine of theta, which we already know, but we could also look at the diagram in order to find that. That's adjacent over hypotenuse. That's going to be x over 2. And now we can notice that the 2 here is going to divide out. We can multiply in the numerator and rewrite it in the format x times 4 minus x squared, and our denominator is simply a value of 2. Now next, let's look at our power-reducing identities. We have 3. Sine squared theta is equal to 1 minus cosine 2 theta divided by 2. Cosine squared theta equals 1 plus cosine 2 theta divided by 2. And tangent squared theta equals 1 minus cosine 2 theta divided by 1 plus cosine 2 theta. Notice that they're called power reducing because we start off with a trig function squared, and then we're able to rewrite it so that we do not end up having a squaring in the expression. Let's look at an example where we're going to utilize one of these formulas. We want to find the exact value of the cosine of 15 degrees. And the way we're going to work this problem is to think about finding cosine squared of 15 degrees. And so we can use the power reducing formula, which can be thought of as 1 plus the cosine of 2 times 15 degrees divided by 2. Let's evaluate further. We'll have 1 plus the cosine of 30 degrees over 2. We're then going to say that this is equivalent to 1 plus the cosine of 30 degrees, you may recall, is positive square root of 3 over 2. And now we're going to multiply both numerator and denominator by 2 to give us a value of 2 plus the square root of 3 divided by 4. Now recall, this is equal to cosine squared of 15 degrees. And so what we can do is take the square root of both sides of that equation in order to come up with a value for the cosine of theta. And we're going to do that next and write it down as the cosine of 15 degrees is equivalent to the square root of 2 plus the square root of 3, all divided by 4. Or we can rewrite that as the square root of 2 plus the square root of 3 divided by the square root of 4, which is 2. Now we're going to verify this result by using a calculator. And so let's go to our calculator and make sure that we're in degree mode. That's one thing to always check. And next, then we're going to go to our home screen, and I'm going to first start off by evaluating the cosine of 15 degrees. That gives me a decimal approximation. And next, I'm going to take the result that we came up with. Now, I'm going to end up with the square root of 2 plus the square root of 3, and I need to close those parentheses twice. And then we're going to have that divided by 2, which gives us, you'll notice, a decimal approximation which appears to be equivalent, and for that reason we can say that it verifies the result that we came up with. Now we're next going to look at a set of identities called the half-angle formulas. Here we have the sine of theta over 2 is equal to plus or minus the square root of 1 minus cosine theta over 2. The cosine of theta over 2 is equal to plus or minus 1 plus the cosine of theta over 2. Now, if you're familiar with those power-reducing formulas, then these are just variations of that, where, remember, those formulas had a theta and a 2 theta. Here we have theta over 2 and theta, that is. Also, those formulas had a squaring, and here we have a square root. So really, this is not a complete set of new formulas, but it's just a variation on what we had previously. We also have formulas that go along with the tangent of theta over 2. We actually have 3 different formulas. The first one is plus or minus the square root of 1 minus cosine theta divided by 1 plus cosine theta is equal to the tangent of theta over 2. And there are 2 more variations of that formula that you might want to become familiar with. Next, we're going to do an example where we're going to use one of those half-angle formulas. If the cosine of theta is equal to negative 7/25, and we know that theta is between 180 degrees and 270 degrees inclusive, let's find the cosine of theta over 2. Here I'm going to start off by writing down the formula that we were looking at previously. We had the cosine of theta over 2 is equal to plus or minus the square root of 1 plus the cosine of theta divided by 2. Now, we're going to start off by thinking about the fact that if theta is between 0 and 180 degrees, between 180 degrees and 270 rather, what does that mean about theta over 2? I can take this inequality and divide all three parts of the inequality by 2. That gives us that theta over 2, the angle in question, is going to be between 90 degrees and 135 degrees. That's important to us because what that indicates is that we're looking at a quadrant 2 angle. And we know that in quadrant 2, we're working with a cosine value which is going to be negative. Therefore, we can evaluate this cosine of theta over 2 as being equivalent to the negative of the square root of 1 plus, here we'll replace the cosine of theta with the value as given, negative 7/25, and we're dividing here by 2. Now, we can simplify this expression further, and in doing so, what we can note is we end up with negative the square root of. One way to simplify would be to multiply both numerator and denominator by 25. Another way to do it would be to actually do this subtraction and then divide the result by 2. Either way we look at it, we come up with a value of 9/25. We're now going to simplify further in order to come up with a result which is a negative square root of 9, which is 3, divided by square root of 25, which is our value of 5. Now we're going to move right along into looking at solutions of trigonometric equations. Here's the example that we're going to be working with. We want to find the solutions to the equation sine of theta over 2 equals 1 on the interval from 0 to 360 degrees. And we're going to be working this problem symbolically, graphically, and numerically. Let's begin by working it symbolically. And in order to do so, what I want to start off with is thinking about the following. If we know that the sine of theta over 2 is equal to 1, then since we're familiar with our sine graph, we know that this value of sine is equal to 1 when the angle that we're working with, in this case theta over 2, is equal to 90 degrees. Now, if theta over 2 is equal to 90 degrees, then multiplying both sides of this equation by 2 gives us that theta must be equal to 180 degrees. We also want to consider this particular equation, and we're going to consider it graphically and numerically, and we're going to do both of those by using our calculators. Let's go to the calculator now, and we're going to go to our y equals screen, and we're going to put into that calculator the side of the equation, which is equivalent to sine of the variable divided by 2. Of course, our variable here is going to be x. Again, we want to make sure that we're in degree mode, which we are. And we're now going to graph this, but we're going to use the window where we're going to have our x minimum as 0, as was indicated in the problem. Our maximum value is going to be 360, and I'm going to use a convenient scale of 90. For our y minimum, I can use a negative 1.5. We know that the minimum value for sine is negative 1. I just went a little bit lower than that. We're going to have a maximum value of, I'll use a positive 1.5, and I'll just use a scale of 1 here. And we're going to press graph. Now, what's being drawn then is the graph of sine of x over 2. Recall in the problem that we were interested in finding out when the sine of x over 2 was equal to 1. And remember, we're trying to notice that we can confirm what we saw symbolically, graphically. Here I just pressed trace because it came up right in the middle of my screen. And notice then that for a value of x equal to 180, we have our y value equal to 1. And that's what we needed to know, is that we actually do end up with that. Another way to verify this would be to look at it numerically. In order to do that, I'm going to use my table. And I'm going to go to table setup, and I'm going to start my table at 0, and I'm going to use a convenient value of 45. Now I have to have a y equals in my calculator in order to use a table. What's going to happen is it's going to evaluate for me the value of sine of this angle over 2. So notice that if I go down to the value of 180, sure enough, I do end up with a y value equal to 1, which is what was needed for the particular problem. Now, we have two sets of identities to look at. The first is called the product to sum identities, and here they are. Now, notice that what's going to occur is we're going to have an expression which is written as a product of trigonometric functions, in this case sine and cosine, and we're going to be able to rewrite each of these as, instead of a product, we're going to be able to write it as a sum. And of course, the sum could either be a sum or a difference in thinking about it as addition of a negative. And as our second set that we're going to be interested in, we're going to be looking at sum to product identities. And this is kind of looking at this backwards. If we're given a sum or a difference, then we can rewrite this so that we end up with a product. Notice we have this cosine function multiplied times this cosine function. Now, in working with these sets of identities, key to being able to do this well is just to recognize the identity when it's needed. So let's look at a couple of examples where we're going to use that. We want to write the following expression as a sum or difference of trigonometric functions. And we're given the sine of 34 degrees multiplied times the cosine of 23 degrees. At the outset, what you want to notice is that we're writing this to begin with as a product, and we're asked to write it instead as a sum or a difference. Let's refer back to those identities that we saw earlier, the product to sum identities. In our particular instance, what we had was the sine of an angle multiplied times the cosine of an angle. And so the formula that we're going to be interested in using will be the one that's given in this third line. Here I have that formula rewritten. And what we're going to do is use the formula in order to evaluate the problem at hand. Sine of 34 degrees multiplied times cosine of 23 degrees. This is going to then be equivalent to 1/2 times the sine of 34 degrees plus 23 degrees plus the sine of 34 degrees minus 23 degrees. Now, we're going to evaluate further and simply add and subtract. So this will be 1/2 times the sine of what will be 57 degrees plus, and here we'll subtract to come up with a sine of, let's see, that's 11 degrees. And so we're able to rewrite this as was asked. Instead of a product, we have it as a sum in this particular example. And let's look at another example in the same manner. Here we want to write the following expression as a product of trigonometric functions. Now notice that what we have given is actually a difference of two cosine functions. Let's look back at our identities, and we want to pick out the identity that's pertinent to the problem. Here we notice the second identity has the format as was needed. So again, I have it rewritten for us, and what we're going to do is use this identity in order to evaluate the cosine of 6t minus the cosine of 5t. Performing the operations as needed, we're going to have that's equal to -2 times the sine of, here we add the two angles together, that will give us 11t divided by 2. And then that's going to be multiplied times the sine, where we subtract the two angles in the order in which was given. So 6t minus 5t would give us simply t over 2. Now, there have been quite a few identities that we've worked with in this session. You're going to need to become familiar with these, and to do so you need to work some problems on your own. Try that now.